Mercury's volcanism is something I've looked into a lot. It's got both effusive volcanisms, that's lavas, and it's got explosive volcanism, when you have lots of volatiles in the magma.
We see these giant areas of basalts on Mercury. They cover a whole part of the northern hemisphere in the polar region, and they're really expansive. And that means that Mercury was pretty hot and pretty active early on in the solar system. This isn't a dead body that we're looking at by any means.
Well, Mercury is really exciting to study because it's a one-plate planet, a single global lithospheric plate, and we think it might have a primary crust like the Moon. But the key is, it turns out to be very, very different. So it's enabled us to really understand something about primary crust, the initial crust, and how it differs from the Moon. And this is really critical to our understanding of the early history of the planets.
Flood basalts inherently involve large volumes. So it seems to me the critical need is to accumulate a large volume of melt somewhere, and then to make it possible to get that up to the surface through the crust at a high enough rate so that you have a high volume flux outpouring. Now, how you do that it calls for a delicate adjustment of the rate of supply of melt from the deeper mantle and the stress state in the crust to let you accumulate the large volume before you eventually generate the fractures that let the melt through to the surface to have the eruption.
I think it tells us that the planet, for a while at least, was very efficient at getting its interior heat out into space via volcanism.
If you have very wide dikes at the time of the eruption, then of course there may be some relaxation of the dike after the stresses which have led to the eruption decay, and they go away when the melt's erupted. But the other thing, of course, is with these very large volume eruptions, which is something which we've inferred for the Mare basalt eruptions on the Moon, that basically you flood the vent, that the end of the eruption does not involve all of the lava flowing well away from the vent to leave it exposed, but that it ponds in the vent at the end of the eruption and simply hides it.
Okay, so a key question is what localizes the outpouring of flood basalts on a planet. In the case of Mercury, we've got good evidence that the older crust, as we see it today, is volcanic, and it looks like it poured out everywhere. We don't see any particular correlation with where that is and any other kinds of landform. But on the case of Mercury, where we have the youngest instances of these flood basalts, the overwhelming majority of them are located beside or inside impact craters and basins. That suggests, or at least makes us think, that there might be some link between the impact process and the eruption of these flood basalts. The eruption of the lavas is not directly due to the impact, and the reason we know this is because if it was, we would expect the lavas to be the exact same age as the impact basin in which they occur. But we know that the floor of that impact basin was exposed to space long enough for it to be impacted with craters, because those craters are barely visible, but visible nonetheless by the lava that poured in later. So that tells us that some amount of geological time elapsed from the formation of the basin to the emplacement of those later lava provinces.
To erupt a very large volume province covering a large area like the plains on Mercury, we're probably going to need dike widths of the order of a few tens of metres. That is wide enough to make sure that the flow of any reasonable, generally mafic melt up to the surface will be turbulent. And of course, once you reach turbulence, the viscosity of the melt doesn't actually matter. So it's the pressure gradient and the width of the dike. But tens of metres seems to be consistent with the sort of fluxes that we infer from the lengths of those flows.
When a planet has a large outflowing of flood basalts, it tells us that at least for a while that planet was very efficient at getting its interior heat out onto its surface and into space.
The interesting thing about Mercury is that it's only really got thrust faults. It's got a few extensional faults, but on the whole what we see is this network all over it of thrust faults which show that the planet has been contracting over time, at least since the late heavy bombardment period, so that's about 3.8 billion years ago. And that's something that's controlled how volcanism particularly occurs on the planet, because it's very difficult for magma to erupt if the surface is in a state of contraction.
That's what's fascinating about this. It does look like all of the large effusive volcanic units on Mercury were placed at around the same time. And that time looks roughly right now to be around 3.6, 3.7 billion years ago. We're still doing work to try and refine those ages, but whatever the actual age happens to be, it looks like all the large units are the same age.
Well, I think Mercury is really interesting from the point of view of its volcanism. It's teaching us that, in fact, the whole planet may have undergone tectonic deformation that enable huge volumes of lava to come out onto the surface over very short periods of time. So when we look at the moon, we see some volcanism, but it's very episodic, whereas on Mercury, it seems to have just come out almost at the same time in these huge expanses. And we don't see any big shield volcanoes or other kinds of things like we see on Mars and the Earth that are typical of slow accretion of lava over long periods of time. So this is telling us something really important about the interior of Mercury, and we really need to understand the interior to understand the overall evolution of the planet.
So one of the primary ways in which the large flood basalt provinces on Mercury are different to the lunar mare, these lava provinces on the moon, is primarily in their volume. The volumes of the lava provinces on Mercury are really enormous, orders of magnitude greater lava per unit emplaced than the mare units, because we see lots of little boundaries and geological divisions in the mare on the moon, implying that not only were they much smaller in volume, but they also erupted over a much longer period of time in the same place. We've no such evidence on Mercury. Instead, what we see is all those lava provinces are put in pretty much geologically instantaneously.
Well, the lava flows on Mercury, they've formed these amazing smooth plains, particularly around the north of the planet, but also in various other places, and particularly within impact craters. So a little bit like when you look up at the moon and you see these darker areas and lighter areas. On the moon, the darker areas are lavas infilling impact craters. Well, something similar has happened on Mercury, although it's not quite so obvious because you don't get that light-dark difference. But the way that you get such smooth plains is to have something that's very, very fluid. So it was hot lava, it was probably very low in silicon compared to eruptions which would cause much more viscous, much more sticky eruptions.
So one of the issues is whether or not they're the same composition if they have the same age. Some of them look like to be different composition to others. We don't have a good sense as exactly why that is. However, we've got a lot of good reason to expect that the interior of Mercury is not homogeneous. It'll have different compositions, both in terms of depth and in spatial lateral extent. So if you imagine you've got all these different sources of magma active, even if they're restricted to impact basins, because they're going to be global in extent, it's not unreasonable to think that you're going to be tapping different kinds of compositions at different parts of the planet. That might explain why they appear to have different compositions, even though they've got similar ages.
When we look at the effusive volcanic products on the surface of Mercury, we actually see chemical differences across the surface, and that can tell us something about the sources in the mantle from which those lava flows have originated, whether they've undergone different amounts of partial melting, different temperature melting, or whether those mantle sources are in fact different to begin with, and that's what's causing the differences we see on the surface.
So an outstanding question that we have to address is the mechanism that's causing the melting of the Mercury mantle in the first place to produce these melts to get them to the surface. I think the greatest likelihood is that it's radioactive decay, because although the mantle of Mercury is much, much smaller proportionally than, say, that of the Earth or Mars or Venus or even the Moon, we still assume that it has some amount of material that's going to decay and radioactively and produce heat. The issue, though, is that because we see these lava flows all have the same age, about 3.7 billion years, that does suggest that around that time Mercury began to exhaust its supply of radiogenic material in its mantle. And that's the process that, because that's the process that led to the melting, that process eventually began to wane, and that's why we don't see any younger lava flows on the surface of Mercury. So it's an important point to make that when we talk about the switching off of global volcanism on Mercury, we're talking about the very large-scale effusive eruptions, huge fire fountains, basalt running over the surface for tens or hundreds of kilometers. Because we see that most of Mercury's crust was built this way, it's an intriguing point that this construction of crust appears to have ended around 3.7 billion years ago. But it's true to say that volcanism on Mercury has persisted beyond that. But it's done so in very, very small scales. We do see at least one patch we know of where the lava may be as young as 1 billion years, but it's deep inside an impact basin. And there's lots of examples of explosive pyroclastic volcanism on Mercury, but it sort of makes sense that that's the kind of volcanism we'd have lasting through Mercury's life, because pyroclastic volcanism is going to have it'll be full of volatiles. It would have more energy that would allow it to drive through the surface of Mercury, which is now in compression because the planet's contracting, that will allow those lavas to reach the surface. But even so, they're still far, far smaller in volume than the expansive flood basalt provinces we see elsewhere on the planet.